All right, great. Thanks, Bill. And welcome to everybody. Thanks a lot for coming. There's a lot of you here. And I should say thanks also, Bill, for the opportunity to do this. I think we've got a chance to make a big difference. And I think everybody in the audience does too. Also, we're, again, videotaping this. We had a lot of people on the wait list that weren't able to get here today, so hopefully they're able to watch. I should say the point of being here and the point of what I'm doing today is really a few things. So, like Justin pointed out, the BAA came out yesterday. I hope you all had a chance to see it. If you didn't, I won't be offended if I see the top of your heads because you're pulling it up on your phone and quickly reading through it. Point of Proposers Day is to help walk you through that, give you some motivation to how we came up with the program, what we're trying to do. Also talk about some of the goals of the program. These are not pulled out of the air. They're the subject of intense discussion over the last several months. And point out what the metrics are, if you're going to be, your proposals to be judged against, and explain basically how to put together a really good proposal. Okay, so also the fact that the BAA came out yesterday, and there's still so many of you here, I think means that it wasn't as bad as we thought it was, or maybe you didn't read it yet. Okay, so PIPES is the first phase 2 ERI program. I've spent a lot of my career looking at the roles of optics in compute, in microelectronics. And there's lots of different places that you can imagine photonics going. Lots of different advantages that you can imagine. But when I look at sort of the 2025, 2030 timeframe, certainly it's really clear that one of the most important roles is going to be for data movement. So we all know that the internet is based on optical communications, and we've seen optics go into the data center and HPC. But really moving forward, we need optics embedded deeper into our systems. PIPES is looking to do that. So let me walk you through first some of the motivation for where we're going here. Okay, now, data movement challenge. Bill talked about how Moore's Law is a hard struggle, getting down to 5 nanometers. And so, while typically we've used feature scaling to get better performance, that's starting to get really hard. It's a very hard race to run. And there's a lot of other vectors we can use to get better performance. When you look at DoD systems and broader commercial systems, they really tend to become an assembly of chips, and we're starting to move data across the system. Here I picked on a little bit machine learning and AI as just one example, but in the DoD we have lots of these. Around 2004, when clock frequency scaling kind of flattened out, we went to high degrees of parallelism on chip. We got multi-core CPUs, GPUs, and a lot of other kinds of systems. And these things actually can communicate pretty well on chip. The cost of data movement, be it in energy or dollars or latency, is actually not too bad. And so we can scale these things up on a single piece of silicon or maybe a few, and we can get really high performance. 5,000 cores on a state-of-the-art NVIDIA GPU. You can make assemblies of these things, and so a DGX box, AI box, allows you to string together on the order of 8 of these on a board. But it gets much harder, right? So you get still better performance when you put these together, but the cost and complexity of the system becomes pretty tricky. When you try and scale up yet farther to system level, you get something like IBM Summit. Fantastic performance, exquisite performance. But again, the cost in terms of energy, cost and complexity and design time means that very few people can afford one of these. And so really, what PIPES is about, it's about looking for a scaling vector that's not scaling smaller and smaller. It's can we get better performance by scaling up and out, right? Putting more blocks of capability together and not being limited by data locality. So all of our systems, we do architecture by trying to keep data local. But if you didn't have that barrier, you could just send data wherever you want, low cost, then you would architect these things different and you'd be able to get better performance. Now, DoD might not want to always do machine learning. There's a lot of other reasons to push on data movement. All right. I decided not to show you a whole lot of Moore's Law curves, but I'm going to show you a couple. This one is sort of under the hood. This is socket bandwidth, the amount of data that comes out of a package as a function of time. And you can see it's been going up exponentially. It hasn't really kept pace with performance on chip, but it's doing pretty well. It hasn't been going up by putting lots and lots of pins on the package. It's been going up by scaling SerDes line rates to where now you're talking 25, 50, maybe 100 gigabit per second per channel. And just to give you kind of a flavor of where we're at, state-of-the-art ICs are running about 10 terabits per second out of a socket. And this is actually sort of a confluence of lots of things. It used to be sort of certain applications, but now we're talking CPUs, GPUs, FPGAs, switch ASICs, and other kinds of ASICs. It's about where we're at. So that seems great. But again, under the hood, what's going on? In green here, I show you the total power per package, and I actually give it an exponential, even though it's been flattening out over time. In sort of a couple hundred watts of what you can pull out of a package. In orange, this is the power just for off-chip I/O. This is running the SerDes. And so you can see, actually, that these things are starting to cross. Now, they can't actually cross. But what you find is that some of these high-end chips, we are running substantial, in some cases more than 50% of the power is just for I/O, not for the function of the chip, right? And so we've essentially hit a crisis. If you scale that out, right, we start to look at many kilowatts in a package. That's not going to happen the way we're doing things today. And the I/O power exceeds the full allocation. Okay, so this then gives me a chance to say, how did we arrive at the main goals of Pipes? Again, plotting that bandwidth out of a package over time. We've got GPUs, CPUs, FPGAs, and ASICs, and again, running at about 10 terabits per second, power going sort of through the roof. And yet we want to go a lot higher. Our goals are looking sort of 5 years out and 10 years out. We want to keep on this track. There's other things we're trying to do too, but sort of high level. 100 terabits per second and a petabit per second out of a package. Right? So these numbers do not come out of nowhere, but they are going to be really hard. In order to get there, or let's say when we get there, the idea is to enable disruptive system scalability through embedded photonic I/O to increase package bandwidth by about 100x. To do so, we're trying to reduce the I/O power by 100x and keep that more or less flat. And also by going photonics, we want to extend the reach of package I/O. Okay, so stepping back and looking at sort of some of the physics underlying this, where we're at today. This is just talking about electronic signaling, and I'm going to keep this super high level. Some of you in the room are far better at this than I am, but I will say that it's really hard to fight against the high-end electronic signaling guys. A lot of smart teams working on this. It's really a cheap way to do things when you're looking at organic materials and copper. However, they are fighting a lot of hard physics battles. If you look at different length scales, so we've got a core IC, a core integrated circuit might be ASIC of some kind. And on chip, there is typically full swing voltage mode signaling. You can't run very far before you need to use repeaters, but it's really energy efficient, right? Sort of femtojoules per bit. If you're in a package, you might want to go across this package and start to go sort of millimeters or so. And in package, it's a little harder. We have lots of different standards and approaches. This might be voltage mode, it might be current mode signaling, serial or parallel, and energy starts to get up there. But then we typically will run out to another SerDes chip, maybe down in a different technology node, and run that across the board. This is where it starts to break down and get really hard. Typically current mode signaling, brand reference, all sorts of fanciness. SerDes, error correction, coding, we start to look at sort of 2 to 20 picojoules per bit. And then if we're lucky, we get to another chip, and if we're unlucky, we have to go off the board, and so maybe we go into an optical transceiver module. So all of these different engineering solutions, I would say, share sort of a common thread, and that is that the physics sets the same trend. No matter what kind of signaling we're looking at, if you look at the energy as a function of performance, and this might be bandwidth down here, it might be reach, things move along pretty smoothly until you start to hit a kink. And this nonlinear increase in energy, the cost, goes up because of loss in your electrical channel or limitations of your transistor frequency. And so what we do is we tend to work sort of design something here. Now, as you look at, say, on-chip or on-board, they have different curves, but they follow the same trend. And what you end up with is sort of a series of dots that follow this trend. Okay, that's the physics, basically. That's where we're at today. If you turn this curve on its head, what you get is what the landscape looks like today. So this is interconnect figure of merit, where figure of merit here I plot as bandwidth density times energy efficiency. So if you think about what's important in pulling bandwidth out of a socket, right? You've got a limited power budget, maybe let's say 100 watts you can pull out of there. You've got a limited size or a limited perimeter. So these are the two numbers that actually limit how much data you can move in and out of a chip. And so figure of merit as a function of reach, sort of millimeters to meters and bigger. So in package, on-board, and off-board signaling. You see this, again, this clear trend that I've pointed out due to generally frequency-dependent loss. These are a bunch of different electrical standards. We have plotted a whole lot more. I didn't want to make it look too complicated, but the sharp slope is pretty significant. If you look at advanced either targets or R&D results, follow the same trend. Once you get off board, typically we're running optical, and this is basically a flat line, right? No frequency dependent loss, but you take a big step to get here, and so low is bad, high is good. And so to put this into a practical sense, this picture is not exactly it, but these dots are roughly something that we do in DoD systems, specific DoD systems. And so if you've got a chip doing something of interest, you want to send data somewhere else, you've got to pay the penalty of sending something across the package, maybe across some flyover cables or something like that, and then into a pluggable or a board-mounted optical transceiver. And what you end up with is adding all of these up, and you get a total that's actually worse than any one of those. All right. So this chart, white space chart, gray space chart here, shows you where we're going. TA1, technical area 1, I'll talk in more detail about what we're doing, is 100 terabit per second out of a package. And in order to do that within sort of an acceptable allocation of power, 1 picojoule per bit. TA2 is looking farther out, 1 petabit per second target, 100 femtojoules per bit. And well, I could say that this is a 4 or 5 order of magnitude improvement over what we're doing today. I think it's maybe more important to look at what this buys you from the other direction, which is to say, what we're trying to do is achieve on-chip or in-package signaling performance and remove locality or remove the length scale, right? So now it doesn't matter if you stay local or if you go 20 meters away. Now there's other things besides density and energy. There's latency and there's cost, right? And so we have latency in our metrics, and the cost, you got to pay for the glass somehow. But really, that's the vision, that we go to a new scaling vector in this program. Okay, so who cares? So there's a lot of people here, so hopefully a lot of you care. But there's really two different areas that I would identify, or at least categorize in terms of user base or people that care about this. First, and I'm going to start at the bottom actually, is what I would call big data, sort of commercial space. So cloud or data center, high performance computing, AI systems, right? And so we have to move a lot of data, and this is generally speaking, but not exclusively, really important to the commercial world. There is machine learning, large-scale emulation, There is computing, advanced parallel systems, things that we want to do commercially and in the DoD. But there are also a whole set of exquisite needs up here, which may not have the same volume drive, but may in fact have bigger needs in terms of I/O bandwidth. And so some of these things look like really high performance sensors, or things that you put at the edge of our networks, or DoD specific things. And so you might have 5G systems, you might have phased array radars that are sending huge bandwidth on and off chip, and want to go reasonably far to get back to a central node. You might otherwise have different types of sensors that have, again, the need for enormous pipes. So in case you didn't get the reference, pipes, right? So we want to send a large amount of data off of these sockets. And so this is another one. Typically, these applications are not going to be the thing that drives the whole community in a certain direction. These things are from a commercial space. And so what we're looking to do in pipes is really impact both. And we're trying to do that by something that was discussed in the BAA as an ecosystem. So the idea is we're not going to just make, say, a better CPU or one better GPU or FPGA or ASIC. What we're going to try and do is establish some access to some domestic capability. And I'll talk a little bit more about this next. But the idea is this probably is the main driver, but we plan to have a path to realize benefits up here. And so create an ecosystem for package-level optical signaling, enabling disruptive advances for AI, phased arrays, sensors, and processing. Okay, so this is in the BAA, but I wanted to call your attention to it because I think it's an important part of the program. And it's really thinking about this technology transition with DoD relevance in mind. So that was part of the goal of ERI, is not just to invest in the technology and let it go. It's to make sure that we realize some differentiating advantage for the things that the DoD and US national security cares about. And so if you look at this need, you can sort of start to think about, well, what's the vision or what's the necessary requirements to make this happen? One of them is capability provided. And so there's a whole supply chain piece in here that I'm not going to get to, but who's exactly responsible for putting these things together? I'd say that DARPA doesn't want to dictate exactly how that plays out, but we do recognize what needs to happen. We need to have photonic components that achieve what we want, and we've identified a lot of the performance in the BAA. Perhaps optical chiplets that are available to other users, maybe IP blocks that are available to other users. We want to define interfaces. Maybe these are open standards, maybe they're not. And we need to have access to both optical and electrical packaging with custom ASICs. Maybe these ASICs are done offshore or done in other places, but we can put them together and make sort of a trusted system with them. We want to bring in DoD users. And so you'll see TA1B is really about DoD applications. And so the idea is we can leverage some of these packaged capabilities that we're creating. But we can also look at how do we enable new ASICs, sensors, and so on with high bandwidth. We might be able to license IP and use some of the onshore capabilities. We're also looking to DoD users to help define the requirements and work together with some of the other performers in the program. We're trying to essentially build bridges between different performers here. And so while it's not expected that everybody makes huge teams, there will obviously be advantage to having teams that cover a lot of things. Over the course of the program, I think we'll actually build stronger relationships. We plan to exercise this ecosystem farther down the road. We talked about this in the BAA as well, but the idea is that we have a demo phase that shows DoD relevance. I'll talk about that a little bit more. And DARPA's role is to identify and fill these technology gaps and to connect these stakeholders. Okay. So now it's going to get a little bit dry, if it wasn't already. I'm going to tell you about the different technical areas. I am specifically supposed to tell you not more than what's in the BAA, and hopefully I don't tell you a whole lot less. If you've got questions, again, put them on your cards, and we'll collect them and try and answer them. We will read your questions out loud, so don't, if you don't want your approach known, don't say, do you think such and such idea is really good, right? Because we will. What else can I say? Let me just keep going, and you can ask questions on your card. Okay, desired outcomes of the program. I felt this was actually important to put in, just so everybody knows sort of what the spirit is of what we're looking for. Technical goals. Number one, we're looking to develop high-value multi-chip modules, MCMs. And these could be ASICs of different kinds, FPGAs, CPUs, GPUs, various things. And when I say high value, you should probably identify how you think is high value, the things that we care about. But these are real, right? We're not looking for just demonstration of point-to-point interconnect that it could be done. We actually want to do it with a lot of bandwidth between them and enable the capability. So MCM with in-package photonic I/O yielding energy, density, and bandwidth more than 10x beyond today, TA1. Number two, create and exercise a path to transition types technologies to DoD users. So this is, again, that ecosystem. Everybody has a role. TA1B is largely the users that are going to be accessing this over the course of the program. Develop scalable manufacturable technologies with performance well beyond current state-of-the-art for 2025 era photonic I/O, TA2 and TA3. I'll get into the details more. Enable domestic capabilities for high-density, low-loss photonic and electronic packaging, largely TA1 and TA3. We expect that solutions are going to maintain familiar form factors consistent with current practice for advanced ICs, including dimensions, electrical interfaces, and thermal management, all PAs. This is called out in the BAA a little more explicitly in terms of footprint. And then technology transition, just to harp on this a little more, we want to enable sustained access for the US government and its contractors to the technologies we develop on the Okay, so program. I'm going to walk through each technical area with a couple slides and show you really what the metrics are, what the program structure looks like, what we're expecting. TA1, this is the big one. At least big one in terms of dollars, but we expect that it's not necessarily the hardest one. TA1, photonically enabled multi-chip modules. The objective, again, this is looking sort of 5-6 years out, maybe shorter if we can get there. Enable disruptive microelectronics by embedding photonics in FPGAs, GPUs, CPUs, basically. We want to drive things down, improve things by about 10x beyond current R&D results, and establish this ecosystem for photonically enabled 2.5D microelectronics. 2.5D is relatively important. The idea, concept is essentially that you have some sort of proxy, or you have a processing core in the middle, and it likely doesn't include your photonics on top. It's not explicitly excluded from the BAA, but this may be advanced node done in a technology that you don't have ability to put photonics in. You're welcome to do so, but we recognize that most MCMs are doing 2.5D. You may put photonics on the side, you may put photonics in the interposer, you may put photonics in the chip. It's up to you. Key metrics and deliverables: enduring domestic capability, 100 terabit per second I/O for real, 1 picojoule per bit efficiency, all in, and I'll talk about that. 20 meter reach, 100 nanosecond latency. And to demonstrate real MCMs. Challenges, there's a lot of challenges. I think you probably know what a lot of these are. How do we look at manufacturing? How do we do fiber coupling? How do we bring the energy down? And so this is what the program looks like, technical area 1 looks like. We have 3 phases, and this is true for almost all the TAs. Phase 1 is largely about the components, 18 months long. Phase 2, about integration, putting things together. And phase 3, about scalability. This is 6.3 funding. And so it has the expectation of generating essentially real stuff at the end, prototype, kind of parts. $35 million roughly anticipated, 42 months, and we anticipate multiple awards in this area. Major deliverables. So these are called out explicitly in the BAA, but just to be a little stronger about it. Phase 2, 2 packaged 10 terabit per second demonstrator units, 1 gigajoule per bit, 2 packaged. Also 10 fully operational MCMs. Phase 3, 2 packaged 100 terabit per second demonstrator units, as well as working towards this pipes ecosystem. We have partnered with some government facilities and folks, and they're going to be actually testing these parts. So they need to be delivered in a way that people can run them. All right, so this is the metric table for TA1. I'm not going to talk about all of them. These are all important, but really, as with all of our programs, I would say that the most important things are at the top, right? And they probably define where we're going. I'm just going to call your attention to a few, but I encourage you to read them all. Aggregate bandwidth, we're working starting at sort of 10 T, 10 terabit per second, and backing off on the energy per bit in phase 1. Pushing bandwidth density, terabit per second per millimeter. In this case, we're talking linear edge density of the package. We have various other metrics, but the idea is manual assembly. So this is showing that the capability works, but it's not necessarily a fully manufacturable process yet. Phase 2, enhanced 10T demo, which means 10 terabit per second, picojoule per bit. And it's also a packaged MCM demo. How much bandwidth you pull out of this MCM is kind of up to you, and it's up to your chip. We are not asking you to develop a new IC to plop in there, and certainly not something that is far beyond state of the art today. Right? So that's not part of the program. The program is identify your ASIC, bring it to the table, and show how photonic I/O will help. And so that total bandwidth is up to you and your ASIC. And we're going to be delivering these. Again, manual assembly of these things is fine, although you have to deliver more units. And then 100 terabit per second. Right? So this is really pushing out beyond where I think even some of the R&D, maybe most of the R&D results are going to be at this point. So hopefully we'll be leading the way. 100 terabit per second out of a package, picojoule per bit. And we want to start moving this towards manufacturable capability. All right, TA1B. So it's a funny name, TA1B. There was no TA1A. And apologize for that. I'll just say it over again so you can hear it. TA1, I explained metrics. TA1B, this is a subtask, and it's different performance, different proposal. TA1B didn't get its own full technical area because it is starting out at least relatively small. Subtask of TA1. Eventually these things are going to be sort of converging. TA1B is looking to apply TA1 technology to a high value mission of interest to the DoD. Essentially I've got proposal elements here, describe the application and interconnect requirement. How's the problem addressed today and what are the limitations of the current approach? Generally this will be an electrical problem, and optics will be a great solution, I imagine. Clearly show the expected benefit to the DoD mission by projecting differential advantage provided to the warfighter. Outline technical requirements for photonically enabled MCMs and optical I/Os, access through the pipes ecosystem. Collaboration with a TA1 performer at the proposal stage is encouraged but not required. It's expected that a TA1 partner will be identified as the program goes on, and that an associate contractor agreement, ACA, we'll talk about that a little bit more, Mike Blackstone will define that a little bit, will be signed no later than the end of phase 1. ACAs are really sort of partnership agreements, I guess I would call them, Mike will correct me, that kind of show how you're going to be working together, but you don't need to do it at the beginning. If you can identify who you would work with, that's great. TA1B. Program structure, it is two relatively short phases, two 12-month phases, where we are defining the concept and the requirements for the technology, and then coming up with a true white paper. What does this demo look like? What are you going to package? What are you going to do with it? Well, we have identified funding for this. We are anticipating moving forward into a demo phase, but this is not part of the current program that you're proposing to. We anticipate that we may select one or more performers for a final 18-month demonstration phase here. And we have the right to solicit and select proposals from folks other than in TA1B. This is again 6-3 funding, 24 months. Because this is a lot of sort of studies and white papers and collaborative meetings, we're anticipating a request not to exceed $600K per award, but multiple awards, and essentially identify what those demos will look like at this point, and then we can move on, hopefully, with partnerships with TA1. All right, TA2, photonics for massive parallelism. This is sort of looking, I guess, at the greenfield out there beyond what we're doing today. How do you get to 100 femtojoules per bit all in? How do you enable a petabit per second out of a socket? We anticipate there's going to be a lot more innovative technology development pieces here, a lot of different architectures, a lot of different approaches, but this is sort of up to the community to identify the way to get there. What we want is I/O that's scalable to a petabit per second, 100x beyond state of the art. We want to achieve 0.1 picojoules per bit efficiency, long reach, short latency, really realizing this vision of bringing the entire world into you. Doesn't matter where things are, we can build a system out of it anywhere. Having said that, this is the one where I feel like we backed off just a touch, and we said, okay, this stuff's not going to be perhaps mature enough to really demonstrate a petabit. If you can do so, go for it. But you will be measured on scaling this thing up to 100 terabits per second. This is still well beyond what any ICs today are generating. We felt that it was actually more important to work on the technology and show the scalability than focus on the scalability at the very beginning. Right? Key challenges. Power reduction is going to be huge. Electronic integration. You can't probably run a few millimeters in a package within your power budget. Component density. Materials integration and packaging complexity. What does it look like? We have various pictures and I just pulled them out because I actually don't want to tell you I think it looks like this and have you do that. Okay? You tell us what it looks like. The idea is to enable like massively distributed parallelism with the TA2, 6.2 type funding. It's got the same schedule, 18-month, 12-12. Roughly $20 million anticipated, multiple awards, major deliverables, 2 packaged demos at the end of phase 2, 2 packaged demos at the end of phase 3. And we go into more detail in the BAA about what these deliverable demonstrator units look like. These are not demonstrated with actual working MCMs. What they're demonstrated with, and we talked about this again, defining, is with likely proxy ICs, so proxy cores in your package that can deliver the kind of bandwidth that we need and can do the testing to verify that you've actually hit what you need. Right? And so creating those proxy ICs is within the scope of the program for both TA1 and TA2. These are the metrics for TA2. Again, I won't walk through them all. You can see the energy per bit gets harder and harder. I've got a slide about this later that I will come back to. But going down to 100 femtojoules per bit, scalable to 1 petabit per second. That means you need to show that the density of all your components, electronics, photonics, packaging, can scale to that. You actually need to demonstrate first. You decide what your length looks like, show the concept works, then scale it up integrate things together, and then show that you have a true path to scalability. Again, other metrics are on here. You should read them. I'm not going to read them all right now. TA3. The TA3 is a little bit funny, and it looks kind of different than the straight point-to-point I/O that we've been talking about. Really, TA3 is saying, you know, if we're really successful in TA1 and TA1B and TA2, we're going to create a whole bunch of problems for ourselves. And we can't tackle all of those problems within this program, but a couple of them we will. The first one is optical packaging, and the second one is reconfigurable switching. And so really the idea is to amplify the impact of pipes technology by helping us build better systems in the future. I encourage everybody on other TAs, TA1, TA2, to work out optical packaging solutions, but I think that people will do the minimum required to get where they need to be. If they do more, great, let us know what that is. But this explicitly pulls out some of the optical packaging, maybe optical routing, maybe low loss connectivity, mass manufacturable I/O that we need going into the future. It may be that we have packages that have 100 fibers coming off or more. We want that to be really low loss because of our power limit. Reconfigurable switching, when we have large numbers of optical pipes in our system, right? Do we want to? How do we reconfigure these systems, or how do we operate them? I believe we will probably get to the point of optical switches. We have some numbers. The way we anticipate this, and we pull it out in the BAA, is that this is an electrically controlled switch, but that optical channels can flow through. Program looks like this. Again, same time frame. Demonstrate your concept in phase 1. Show an integrated capability in phase 2, and demonstrate that you can scale this up in phase 3. TA3 seeks high-risk, high-payoff approaches to enable future scaling beyond what will be developed elsewhere within the program. So we're really looking for, we've got some metrics. You need to address those metrics, but looking at things that might fall outside the scope of what people are doing in the other TAs. 6.2 funding, $10 million, multiple awards, major deliverables. Starts out by demonstrating results likely in the lab or in the packaging facility or wherever you're at, showing how you're going to commercialize or transition this stuff. And then particularly for the switching thrust, give us packaged units. Packaging thrust, something that we asked for and essentially hope for, but is not anticipated from everybody, is that you've got a role to play in this ecosystem. And so if there is an onshore capability that delivers optical chiplets, IP blocks, somebody from the DoD community has a great ASIC and they want to package it together, we would like to be able to do that domestically, onshore. And so you can think of this as sort of helping to enable that. If that's what you're looking to do, let us know in the proposal. That would be great. Because there are a lot of different approaches, some of them are high maturity at this point, some of them are low. We have proposer-defined metrics for phase 1 and phase 2, but we have actually pretty difficult prescribed metrics in phase 3. And so anything that you propose in either of these thrusts actually needs to have a clear path to meeting these. And so we don't want to have metrics that suddenly get, that are easy, and then exceedingly hard to get to phase 3. Right? Let me walk through them. Volume compatible optical packaging capability. This is, anticipating perhaps 1,000 fibers out of a package. These are not going to be assembled by hand. Going to be automated alignment and attached. We're targeting insertion loss of these fibers below 0.25 dB and broad spectral bands. If you've got ideas that are, we call this out actually exclusively, we're talking about fibers here. If you have ideas that are not fibers, that can still be interesting. We talk about optical channels. Down here, reconfigurable optical switching technologies. We're looking for an integrated switch that can scale up to 1,000 by 1,000. There are other technologies that may scale not as well. You see where we're targeting. Let us know how you can get there, or what it would take to get there, or what the value of what you're proposing is, given this target. We need really low insertion loss, fiber-to-fiber insertion loss below 3 dB. I can imagine multiple different ways to get there. Switch reconfiguration time below 10 microseconds. Not bit level switching or anything like that. Broad spectral bandwidth, we anticipate a lot of WDM approaches elsewhere. Switch power, so in the package switch of 100 watts. And a note on link budget. This applies to TA1 and TA2 in particular. And we call this out in the proposal. You should talk about this. You should give us a chart, I believe we asked for. We want to know what's in your power budget, how you are going to hit 100 femtojoules per bit or picojoules per bit or whatever is the number that you're looking for. And you have to include everything. Right? So we are talking from, here we call it a core IC, and we use that language. You've got some rail-to-rail signal here, and you have to get to a rail-to-rail signal over here. Right? So it counts error correction and SerDes and driving maybe to a chiplet, and what is the transmit and receive drivers, and if you've got an on-chip or off-chip source, what does that laser consume? It is all-inclusive. Thermal tuning, DSP, CDR, equalization. Some of these you might be amortizing over multiple channels. Important dates. VAA posted yesterday. You're all here today. Abstract phase. So we have an abstract phase, and we encourage you guys to use it. Specific requirements on the abstract are in the VAA as far as length and what you should include. We will get all of the abstracts and provide feedback. We don't have a date on there. We will do it. Mike will talk about it. Great. But we will provide feedback with enough time that you can hit the proposal due date, which is January 17th, 1 p.m. Eastern Time. I should point out we have frequently asked questions. FAQ will be starting probably this week. Maybe next week will be posted online. Every question that you guys ask on cards, questions that people email in, we will post the question and the answer for everybody to see. This will be sort of accumulated over time. The deadline for asking questions is January 3rd. Proposal due date, January 17th. But as with some other ERI programs, we have a rolling deadline this time. I want to point out that this is in bold and big for a reason. This is when we want proposals to come in. We will be evaluating them shortly after. Proposals that come in afterwards, up until March 1st, if deemed compliant, those proposals will be reviewed at the government's discretion, contingent upon the availability of funds. I would prefer all of the great proposals come in here. It would be sad to have a good proposal come in and have no availability of funds because we already spent them all. Proposals are warned that the likelihood of available funding is greatly reduced for proposals submitted after the initial closing deadline. Given this deadline and Mike and his team working really hard, anticipated performance start is July 29th. Okay, I think this is my last slide, and I wanted to just highlight the evaluation criteria. So, just to be clear, there's a VAA. It asks for everything that we are looking for. Your proposals will be judged against the VAA. And so, it would be better if you don't propose what you think the program should be. Propose what the program is, and your proposal will be evaluated against these criteria by a panel of government folks. Overall scientific and technical merit. Demonstrate that the proposed technical approach is innovative, feasible, achievable, and complete. Describe how the proposed approach will achieve each program metric with sufficient detail in supporting experimental measurements, modeling, calculations, and simulation. Number 2, potential contribution and relevance to the Power Commission. So you should note that this is not just boilerplate. all of the words in there are intentional. There's an emphasis on contribution to U.S. national security and U.S. technological capabilities, consistent with the ERI Phase 2 discussion that Bill shared. You should discuss how the proposed effort addresses the ERI goals of technology transition and facilitating access to pipes technologies to the DOE. Number 3 is cost realism. Ensure proposed costs are realistic for the technical and management approach that you propose, and accurately reflect the goals and objectives of the solicitation. And finally, please verify when you put together the cost proposal, we actually have to read it. It's very detailed, and a lot of people, there's a large mix of what we get in the cost proposals. Make sure that you give us enough detail so that we know where it comes from. Make sure that it's complete, covers everything, and make sure that it's consistent with what you propose to do. There's also in the BA a template for a simplified chart that will help us make sure that that is consistent also with the cost proposal.